Hey guys, some mysteries are written in sound, deep, distant echoes rising from the bottom of the ocean. Others are carved into time itself, numbers that don't quite add up, signals that drift where physics says they shouldn't. In this collection, we listen for the world's quietest questions. The hum of deep water, the chill of space, the slow ticking of things built to outlast us. We'll hear a noise that shook the Pacific, a pair of spacecraft that refused to follow their own equations, and a cold stain stretched across the fabric of the cosmos. We'll travel beneath Antarctic ice, across the Baltic Sea floor, and through the high plains where the sky filled with impossible drones. And finally, we'll stand before walls of coral and a clock meant to count not years, but millennia. These are stories of sound and silence, distance and time, places where science meets its limits and wonder quietly takes over. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And let me know in the comments where you're listening from and what was the last thing you remember before sleep pulled you under. Now dim the lights and let's ease into tonight's journey together. A calm sea under the southern sky, an empty stretch of water that should have been quiet, and far below, a line of underwater microphones listening to the deep. Then came a sound no one expected. This story is The Bloop, the deepest sound on Earth. In the late 1990s, the National Oceanic and Atmospheric Administration inherited a listening post beneath the waves. It had started life during the Cold War as a network of seafloor microphones stretched across ocean basins to track very quiet submarines. After the war years, many of those instruments were turned towards science. Oceanographers listened for whales, storms, undersea earthquakes, and the countless small sounds that fill the water column. They learned to read the ocean like a radio band. Low tones traveled especially far inside a natural layer called the deep sound channel, where cold water and pressure guide sound for thousands of miles with little loss. On paper and on glowing screens, the ocean wrote in lines. In 1997, the network kept a steady watch across the Pacific, including stations in the far south, where the water is cold enough to sharpen the breath, and the winds can build for days without touching land. The pace of work was orderly. Check the reels, mark the events, catalog the unusual. On an otherwise ordinary stretch of days, a technician rolled tape and saw a shape in the spectrogram that did not fit into any of the usual bins. It rose in frequency over less than a minute, starting low, then climbing like a hand gliding up the neck of a cello, smooth and quick before falling silent. It was strong, so strong that it registered on sensors placed thousands of miles apart. They nicknamed it simply the Bloop. The nickname stuck, but the details were not cute. This was not a little pop near the surface. It came from somewhere in the deep South Pacific, far west of South America, in water that, even at the height of summer, hovers near the freezing point, about 0 degrees Celsius or 32 degrees Fahrenheit. The signal did not arrive on one microphone only. It came in staggered across the network, each arrival separated by the time sound needs to cross such distances. With those delays and some quiet math, the team could triangulate. The best fit put the source in a lonely patch of ocean closer to the Antarctic circles than to any shipping lane. There are a few hard facts about that minute that matter. First, the sound was very low in pitch, mostly below the range of human hearing when played in real time. To be heard clearly, recordings need to be sped up. That change produced the quick, comic syllable that gave the event its name. But the true sound in the water would have felt more like a surge than a syllable. Second, the amplitude was remarkable. The oceanographers were used to hearing the deep voices of blue whales spread for hundreds of miles. This signal crossed much more than that. Third, it happened more than once that year. The network logged several events with the same rising shape from the same general region. Those watchers knew the catalog well, and they began the usual process of elimination. Ships make sound, but the noise of a large propeller is mechanical and even, with distinct harmonic bands. Submarines are engineered to be quieter than the sea around them. None of those matched the shape on the page. Seafloor earthquakes crack like snapped timber and rumble low without the quick upward sweep. Volcanic tremors can carry a steady buzz, sometimes for hours. Again, not a match. Storms raise a curtain of hiss, and lightning strikes produce sharp snaps, not these long rising tones. Animals, then? The idea came fast because of the sound's shape. Whales sing in upsweeps and downsweeps, and many of those lines look familiar on a spectrogram. A playful thought brushed across the lab. If this were a living throat, that animal would be larger than any known whale. The power in the signal suggested a source stronger than a blue whale by a comfortable margin. That alone strained belief. The blue whale is already at the limit of what a body can carry and feed in the open ocean. Still, the human mind makes patterns. People outside the lab picked up the story, and after the sound's location was plotted on a simple map, someone noticed how close it sat to the imagined site of an ancient city from a 20th century horror story. It made for a headline. Inside the agency, the work was less amused. They kept listening and began to collect not just one odd event, but a family of them. Across the 90s and into the 2000s, technicians and scientists tagged other strange sounds with plain nicknames. Slowdown, Train, Julia, each had a personality. Slow down descended slowly in pitch, like a heavy wheel easing to a stop. Train sounded as if a long freight was rumbling by somewhere unseen. Julia arrived as a long moan. Some of those were tied to volcanic fields in the deep. The seasonal signature of one long-running signal lined up with the southern spring and autumn, often near a chain of sea mounts. But more and more, the strongest, shortest events pointed south, toward the ice. Here's where the story moves from spectrogram to fieldwork. Around 2008, research cruises set hydrophones near the edge of the Antarctic pack ice and along routes where giant icebergs drift. Those microphones captured something that brought the bloop into focus. When a vast slab of ice cracked, the sound was not a single bang. It was a complex rising call, starting with low groans as a fracture opened, then sweeping upward as the two sides slid against each other, sometimes with water flooding the gap. When an iceberg grounded on the seafloor and scraped free, the audio painted a similar curve, low at first, then accelerating as more of the underside met rock and the friction pattern changed. The cold matters. Seawater at those latitudes hovers around -2 degrees Celsius or 28 degrees Fahrenheit because of the salt content. Air temperatures can dip far below that in winter nights and rise a little above freezing by day in summer. That swing drives stress fractures in the ice. Tides and wind then apply force. With each shove and release, the ice shudders and speaks. A strong fracture can be heard, not just by the seals and penguins on the surface, but across an entire ocean basin. By 2012, after many seasons of comparison and new recordings, the leading view inside the National Oceanic and Atmospheric Administration was straightforward. The bloop and several of its cousins matched the acoustic fingerprint of large ice events. In plain terms, an iceberg cracked or scraped, and the water carried the sound. It is not the only possible explanation, but it fits the data and it fits the place. There are reasons this answer is persuasive. The location aligns with the drifting paths of giant icebergs shed from the big shelves. The timing of similar sounds is seasonal. The rising shape is better explained by changing friction or widening cracks than by any known animal behavior. The amplitude no longer demands a creature larger than a whale. It merely requires a vast, rigid object under great stress, which is exactly what an iceberg is. And when listening posts sat nearer the ice with modern instruments, they heard the same shapes with direct visual confirmation of ice motion from satellites. Skeptics of the ice idea point out that the original sound traveled so far and carried the tone of a voice. Nah, not a crack. That is fair to say when you hear the sped-up version, the one you can play on a speaker in a room. In the water, the low pitch is closer to a long moan than to a cartoon blip. The deep sound channel smooths rough edges. A messy event becomes a streak of tone. The animal hypothesis still attracts the imagination. If an unknown species called in the abyss with lungs or resonant sacs more powerful than any known whale, it would help to explain not only the bloop, but also some of the other nameless voices that occasionally roll through the network. The counterpoint is practical. There have been decades of visual surveys, tagging studies, and passive listening. The ocean hides things, but it rarely hides giants that sing. Man-made explanations deserve a brief mention. Underwater construction can be loud, but drilling and pile driving tend to be near coasts and leave a comb of steady frequencies rather than a smooth glide. Military sources in the open ocean are designed to avoid notice, and, when they are heard, often carry the stamp of human craft, regularity, repetition, narrow bands. Nothing about the bloop suggests a test range or a machine. One small footnote is worth keeping near the end, not as an anchor, but as a reminder of how stories grow. The location assigned to the bloop sits not very far from a set of made-up coordinates in a famous work of fiction about ruins and sea and madness. That coincidence colored many early retellings. It helps to know it and then to lay it aside. The ocean gives enough reality as it is. If you lay the pieces on a table, the year, the source region, the remarkable reach, the rising shape, the family of similar sounds, the later field recordings near the ice, a likely chain of events emerges. Picture a winter-scarred iceberg moving north into a strip of slightly warmer water. Tides pull. Wind pushes. Along its base, a tongue of ice meets a hidden ridge on the seafloor. The berg grinds and catches. Stress climbs inside it, like a bending bow. A fracture opens. The tone sweeps up as the crack runs and accelerates. And for less than a minute, the ocean sings in a way you can see on paper, even if you cannot hear it with your own ears. Then the tone cuts off. The iceberg eases free, and the basin goes back to its normal chorus. That chain is not certain the way a ship's log is certain, with fuel counts and crew names and a berth number. It is, however, solid enough for the people who listen to the ocean for a living. They still monitor the South. Each year has its own character. Some seasons bring many ice songs, some are quiet. A long, faint background signal called upsweep continues near a volcanic chain and remains under study. There are always mysteries left. Out on the water, the deep sound channel keeps carrying voices you and I will never hear directly. A whale calls, a storm front hisses, a distant cliff lets go and drops rock into the sea. And sometimes, far from any land, and under a sky that feels too large for human names, ice breaks and speaks in a tone that can cross an ocean. That tone is what we remember as the bloop, not a monster, but a moment when the cold geometry of ice and water turned into sound, traveled for a day through the calm heart of the Pacific, and arrived in a quiet room as a rising line that made a few people lean forward and listen twice. Some mysteries announce themselves not with spectacle, but with a number that refuses to behave. Far from home, in the quiet beyond the giant planets, two small machines began to drift in a way no one had predicted. This is the Pioneer anomaly, when physics glitched. In the early 1970s, the United States sent two identical probes on long, looping paths through the outer planets. The first left in 1972, the second in 1973. Each carried a broad white antenna dish, a shallow bowl always turned toward Earth. They spun to stay stable, like tops balanced on a fingertip. Power came from warm, plutonium-fed generators that turned heat into electricity. There were no solar panels out there. The sun would be a distant coin, the light too thin to be useful. Their first task was close-up work at Jupiter, and for the second craft, Saturn II. These were flybys, not stops. Gravity bent their paths and flung them outward, and when the work near the planets was done, both machines coasted into deep space on escape tracks. The distances soon became hard to fathom. Signals took hours to cross the gap. The receivers back on Earth were giant radio dishes spread across deserts and hills, and the way those dishes judged distance and speed was simple in principle. Listen to the tone of the returning signal. If the craft were drifting closer or farther, the pitch would shift slightly. That is how sailors once judged a train, by its horn in the distance. Here it was done with far more precision, against a background of silence only deep space can provide. For many years, the numbers lined up with the prediction books. Engineers accounted for the pressure of sunlight, the faint drag of interplanetary dust, the pull of the known planets, even the tiny recoil when the craft rotated their antenna or heated a panel on one side. The residuals, the leftover bits after calculation, were small and messy, just the noise of real machines in a real universe. Then analysts noticed that something remained after all the usual reasons were removed. It was not a spike or a sudden swerve. It was a steady, inward tug, as if a hand were gently pressing the probes back toward the sun. The effect was tiny in everyday terms, but persistent in the math. Over weeks and months, it did not wash out. It looked close to constant. It appeared in both spacecraft, measured across years, and it seemed to show up most cleanly once the probes had passed well beyond Saturn, tens of Earth-Sun distances away. The finding was first raised quietly in the 1980s inside the navigation teams, then presented more formally in the 1990s. The way the anomaly surfaced felt like a whisper that would not go away. The signal tone from the probes was just a touch higher than expected, as if they were slowing slightly more than the models allowed. In human terms, it was the difference between arriving a few seconds late after a drive across a continent. In the team's work, those seconds mattered. Because the craft were spinning for stability, their behavior ruled out some simple fixes. A steady gas leak from one thruster would have been averaged out by the spin. The pressure of sunlight fell with distance and could not produce a nearly constant push so far from the sun. Drag from dust was too weak in those empty regions, and if it had been stronger than believed, it should have affected comets and planets in ways astronomers would already have seen. So the detective work began in earnest. Engineers laid out the design of the probes again. The dish, the long booms holding the warm generators on either side, the boxy electronics bay covered by a set of louvered panels that opened when hot and closed when cold. They went back to the original telemetry, the housekeeping data telling how hot each part was, how much power the generators produced, when heaters switched on or off. These records were not all on modern drives. Some sat on old reels and tapes stored in boxes, written in formats no current machine could read. A small group spent years recovering, cleaning, and reinterpreting those numbers. Outside the lab, a different kind of speculation grew. Some physicists proposed that gravity might behave a little differently at very low accelerations, suggesting that the old equations were only approximations that broke down in the far reaches. Others spoke of undetected mass in the outer system, a broad belt of small ice and rock objects that, in bulk, might tug the probes sunward. A few even wondered about the influence of dark matter, the unseen component thought to weave through galaxies. These ideas had enthusiasm, and they had critiques. A change in gravity strong enough to bend the path of these two machines should also shift the motions of planets and moons by a measurable amount, and those motions are tracked with exquisite care. A great, even belt of matter might pull, yes, but it would then also nudge many other wanderers the same way, and that pattern did not show up. The drift of the two probes looked like a special case. More down-to-earth explanations had their day as well. Perhaps the timekeeping on Earth was introducing a bias, or the way the receivers processed the tone shifted the result. Maybe the antenna dish was interacting with the solar wind in some subtle way. Each idea could be tested against decades of data, and most fell away after careful review. One hypothesis refused to go quietly because it lived inside the craft themselves. Heat. Every watt of heat a spacecraft emits pushes it in the opposite direction. In the same way, a flashlight experiences a minute recoil when it shines. Most of the heat on these probes came from those warm plutonium cores mounted at the tips of the long booms. Another portion came from the electronics inside the main body, the part that needed to stay within livable temperatures. In an environment near minus 270 degrees Celsius, or about minus 454 degrees Fahrenheit. If that heat left the craft evenly in all directions, it would cancel out. But if the shape of the craft, the reflective face of the antenna, and the placement of vents and louvers caused a little more heat to flow one way than another, the recoil would be a tiny, steady push. The awkward part was proving it. Heat is sneaky. It reflects from surfaces. It leaks through seams. It travels through brackets and wires. To see whether an uneven glow could imitate a new law of gravity, the team needed to know not only how much warmth was produced year by year, but also how it left the body, which parts radiated most, which surfaces acted like mirrors when the louver doors were open, and by how much. Around 2010, after a decade of archiving and reconstruction, the picture sharpened. The probe's power output had been declining gently as the plutonium aged. If heat recoil was the source of the extra slowing, then the anomaly should also slowly decline. When the data were reprocessed with this in mind, that is what emerged. A small fading of the effect over time, just the sort of change you would expect if the last warm breaths of the machines were pushing them backward. A detailed computer model, less a glossy animation than a stack of engineering notes turned into numbers, showed that the large dish would reflect a portion of the internal heat forward, adding to the asymmetry. The long booms carrying the generators took some heat away to the sides, but the geometry was not perfect. Even a few percent imbalance integrated over years could do the job. In the year 2012, a thorough analysis pulled the threads together. Using the recovered engineering data, the team calculated the recoil from thermal radiation and compared it to the observed drift. The match was close enough that most of the anomaly was explained without invoking new physics. A couple of independent efforts, using different methods to estimate heat flow, reached similar conclusions. It was a quiet answer to a loud question. Not everyone felt satisfied. A small number of researchers argued that the early years of the anomaly looked too tidy, too constant, to be only heat. They pointed to tiny seasonal wiggles in the signal, linked to the geometry between Earth and the probes, and asked whether some unmodeled property of the radio link might be in play. The counterpoint was straightforward. Those wiggles fit known alignments and measurement rhythms, and the main effect still grew and faded with heat output as expected. No law had to bend. That leaves a choice of how to tell the story. One way says that the outer darkness confronted us with a flaw in our understanding, and we stepped toward a new chapter of gravity. Another says that our models of the craft were incomplete, and when we accounted for every watt and every reflection off a painted panel, the puzzle resolved into ordinary physics with a human twist. The second telling is the one most specialists now accept. Here are a few details worth keeping. The anomaly appeared in both probes, even though they took different final paths. That argued against a local environmental cause. The craft were spin stabilized, which made short, jerky forces average away over a full rotation, leaving a signature that looked constant. The probe's last calls home came years apart. The second one fell silent in the mid-1990s. The first held on until the early 2000s. But the odd drift persisted in each as long as the data ran cleanly. And in the end, the final explanation did not require exotic matter or new constants, just a careful accounting of heat in the cold. If you line up the facts, launch, sling past the giants, steady radio contact over billions of miles, a stubborn sunward drift, models tested and discarded, archives dug up, warmth mapped and reconciled, you can build a plausible chain. A probe heads into the deep, its body warm, inside a universe near minus 270 degrees Celsius, or minus 454 degrees Fahrenheit. The big antenna faces home, and like a shield, it reflects some of that warmth forward. The rest leaks out through panels and seams in patterns that are not perfectly even. The recoil is tiny, steady, and always there. Measured across decades, it looks like a new tug. But when power fades, the push fades with it. The numbers settle. There are other puzzles in spaceflight that keep their edge. Small speed changes during close passes of Earth, strange noises in long-lived instruments. And not everyone resolves as neatly as this. But the Pioneer anomaly offers a useful lesson wrapped in a quiet image. In the coldest place we send our work, the last, gentle warmth of a machine can steer its fate. Somewhere far beyond the orbit of Pluto, the first of those probes continues to drift, its dish still pointing back at a world it can no longer reach. The second wanders too, on a slightly different path. In the end, the force that nudged them off our ledgers was not a new law written into the fabric of the cosmos, but the simple physics of heat leaving a human-made shell into endless night. That is how physics glitched here, not by breaking, but by reminding us to count everything, even the warmth of our own touch. Sometimes the strangest findings arrive in the quietest work. No crowds, no spectacle, just numbers on a screen, and a sky that does not change its mind quickly. That is how the cold spot in the cosmic microwave background came into focus. A soft bruise on the oldest light we can see, faint but stubborn, and still not fully explained. To understand why this patch matters, step back to the oldest light in the universe, the cosmic microwave background, often called the afterglow of the Big Bang. It is a thin wash of microwave light that fills the sky in every direction. Its temperature is close to minus 270 degrees Celsius, or about minus 454 degrees Fahrenheit, with tiny ripples only a few parts in 100,000 above or below that average. Those ripples are the seeds of everything that would later form galaxies and clusters. So mapping them is like taking the universe's first portrait. In the early 2000s, a satellite from the United States Space Agency called the Wilkinson Microwave Anisotropy Probe traced that portrait with far greater clarity than before. Later, a European mission named Planck sharpened it even more. The maps revealed the usual pattern: a mottled texture of small, warm, and cool spots spread almost evenly across the sky. Just what the standard picture of cosmic growth expects, except for one region. In the constellation Eridanus, the data showed a broad, cool patch, a few degrees across, which is roughly the width of 10 full moons lined up. It was not just slightly low. When analyzed with mathematical tools designed to pick out features at specific scales, the patch stood out. Imagine a gentle dip with a faint warm ring girdling it near the edges. That circular pattern made it feel less like background clutter and more like a particular coherent feature. The first reports marked it as unusual, perhaps unlikely in a random field. The odds quoted at the time suggested a low chance of stumbling on such a deep, cool patch when scanning the entire sky. But odds are a slippery friend when you look everywhere. If you examine enough pixels with enough filters, rare things show up. This is why confirmation mattered. When the European mission released its data about a decade later, the cool region was still there. It was measured at multiple microwave colors, the sort of cross-check that usually strips away interference from our own galaxy. It survived tests that try to see whether the feature fades when you change how you clean the data. It persisted, though the later work described it in more cautious terms. If the early interpretation made it sound like a showstopper, the later one said, "It is odd, it is real in the maps, and its statistical weight is significant, but not a signal of new physics all by itself." So what could make a broad, cool patch in the oldest light? One family of ideas starts nearby, on the way the light travels to us. The afterglow left the early universe long before stars and galaxies formed. On its way across billions of years, it passed through great underdense regions, vast cosmic bubbles with fewer galaxies than average. In a universe whose expansion is speeding up, light that falls into a deep gravitational basin, then climbs out, ends up giving back a little more energy than it gained. The reverse is true for a great emptiness. Light crossing a very large void can lose a trace of energy, arriving a touch cooler than it started. This late-time energy loss effect is hard to see for any single void. You usually need many measurements stacked together. But what if, by chance, along the line of sight to Eridanus, there was a very large, very empty region? In 2014, a team Stitching together infrared and optical surveys reported exactly that. A spread out underdensity, hundreds of millions of light years wide, centered roughly a couple of billion light years from us. They called it a supervoid and argued that its presence could account for a portion of the cool patch. Follow-up work mapped galaxies in that direction and found further hints of a lack, not a clean hole, more like a string of underfilled zones aligned along the same sight line. There is a catch. Calculations suggest that even an unusually large emptiness cannot by itself create a cool patch as deep as the one observed, not without stretching the accepted rules. The timing of the universe's acceleration, the depth of the void, and the exact path of light all matter. And when you add them up with conservative numbers, the void's imprint falls short. Supporters reply that the line of sight may hold multiple voids that add together, and that the rough estimates may be undercounting their combined effect. Skeptics note that the depth you would need is greater than galaxy surveys truly show. The balance of evidence points to a contribution from emptiness, but probably not the whole story. Another set of ideas reaches back to the earliest moments. Some theoretical models predict that the fabric of space could have left behind rare defects, not cracks in the ordinary sense, but topological quirks called textures that would imprint a distinctive cold or hot feature when the afterglow passed through them. If a texture sits along our line of sight in Eridanus, it could create a circular cold region with a surrounding warm ring. This would produce a specific pattern in the polarization of the light, as well as in its temperature. Observers looked for that pattern and did not find a clear match. The absence of that signal does not kill the idea, but it weakens it. And while it is tempting to tie one dramatic feature to one dramatic cause, the broader sky looks too tidy for textures to be common. More adventurous proposals mention bubble collisions, a scenario where our patch of space rubbed against another in the early inflating universe, leaving a circular scar in the map. If true, that would be thrilling. Tests for this kind of collision look for concentric circles, unusual ripples, or specific polarization signatures. The searches so far have not turned up convincing companions to the Eridanus feature, nor a consistent polarization clue that would lift it out of the ordinary. A simpler explanation is that the cool patch is a statistical fluke. In the standard picture, the variations in the afterglow are like a random field with known rules. Even in such a field, anomalies occur simply because rare does not mean impossible. If you tile the entire sky and apply different smoothing scales, you are effectively drawing many tickets from a large lottery. Now and then, one draw looks special. Several studies argue that when you count those draws properly, the odds of finding a patch as odd as the Eridanus feature are not breathtaking, low, but not astonishing. That said, one aspect continues to nag. The ring-like warm edge around the cool center looks organized, and organized patterns in a random field tend to raise eyebrows. It nudges people to keep looking. Could it be a mistake? A leftover from the way the maps were made? This is the first possibility scientists try to eliminate. The cool region appears in data from two different missions, built by different teams and flown a decade apart. It shows up across multiple microwave colors. Removing dust from our galaxy is always a delicate business, but the patch sits away from the worst parts of the Milky Way plane, and frequency tests suggest that known foregrounds are not the driver. Map-making errors tend to leave scars that repeat in well-known places or angles. This feature does not follow those patterns. It is hard to prove that every kind of systematic error is absent, yet the redundancy in the observations makes a simple artifact unlikely. If you lay the findings out on the table, a cautious picture emerges. The cool patch is real in the data. It is larger and deeper than typical ripples, but not outside the possible for a random field if you consider how many chances you gave yourself to find something. A real underdensity along the line of sight likely deepens the effect, perhaps by a small but non-negligible amount. The more exotic ideas, ancient textures or a brush with another cosmic bubble, remain possible in principle, but lack strong supporting signatures in the surrounding sky. And the careful work of checking instruments, beam shapes, and foreground cleaning has not delivered a mundane, fixable error. Here is a quiet chain of events that fits many of the facts. In the early universe, random variations set the initial conditions for everything we see. Those variations, when scaled up to a full sky, include rare but lawful extremes. One such extreme happened to land in the Eridanus direction, producing a cool region with a subtle ring. Billions of years later, as light from the afterglow crossed a series of underfilled zones on its way to us, it lost a little extra energy, darkening the patch by a small amount. When our instruments finally became sharp enough to read that ancient light, the patch stood out, not because the universe broke its own rules, but because we are finally able to see the edges of what those rules allow. There is one more layer that keeps the conversation open. The afterglow carries not just temperature information, but also a delicate pattern in the direction the light waves prefer to vibrate. Some theories predict a definite relationship between the cold patch and that polarization pattern. Measurements so far have not found a matching signature in the Eridanus region. That absence leans against early universe oddities and quietly supports the idea that this may be a statistical outlier, perhaps helped along by nearby structure. But even here, the measurements come with limits, and future maps may refine the picture. You can think of the sky map as a sheet of faintly textured paper. Most of the grain is even, the texture what you would expect from a careful machine. And then there is one dimple that draws the eye. You run your finger over it. It is real. You check the press. The process seems sound. You pull the sheet into the light. You see a slight ring around the dimple. You cannot say whether it was in the paper from the start, or picked up a mark along the way, or both. The cold spot remains that dimple. A measured, persistent oddity in the oldest light, likely born from the same randomness that governs the rest, perhaps deepened by a long, sparse stretch of space. The more dramatic answers have not been ruled out entirely, and that is part of the quiet pull here. We keep testing, not because we need miracles, but because the universe sometimes hides its lessons in the margins. For now, when scientists unfold the all-sky portrait and set it on the table, a soft oval in Eridanus still looks back. It is a simple thing. A patch a few degrees wide, cooler than its surroundings by a few parts in 100,000. And yet, it has carried years of careful work on its shoulders. In a field built on statistics and patience, that is often how mysteries live. Not in fireworks, but in a spot that refuses to turn ordinary no matter how many times you measure it. December, the middle of the 20th century. A white plateau that seemed endless. A small team on tractors and sledges, listening for echoes with simple instruments lowered into the snow. They heard shapes in the ice that did not match rock. Then, decades later, aircraft sent radio pulses into the depths, and a curious brightness came back, smooth, flat, and wider than anyone expected. That was the beginning of what we now call the subglacial lakes of Antarctica, hidden ecosystems. Antarctica is a continent smoothed by ice, not by quiet. The ice sheet there is thick enough to swallow mountain ranges. In places, it is more than 2 miles deep. Under that weight, the bottom of the ice is pressed hard against the bedrock, warmed slightly by the heat rising from the planet's crust. Pressure lowers the freezing point. Heat from the ground adds the last degree or two. Where the ice slides over gentle slopes, the friction helps. Meltwater forms, gathers, and, if conditions allow, makes lakes, not puddles. Some are as large as inland seas, sealed beneath ice that never sees summer. Hints surfaced in the late 1950s, when over-snow traverses crossed the high interior, with field equipment that read echo times through the ice. They logged odd returns, as if the ice sat on something smooth. In the 1990s, satellite maps and airborne radar made the picture clear. There was a giant hidden body of water beneath the central plateau, lying under more than 2 miles of ice, roughly 150 miles long and 30 miles wide. The ice directly above it had a telltale flatness, a soft tabletop in a land of hills. The water under that patch is cold, near the melting point under pressure, roughly 0 degrees Celsius, which is about 32 degrees Fahrenheit. The station nearby once recorded the coldest surface air temperature ever measured on Earth, about minus 89 degrees Celsius, or minus 110 degrees Fahrenheit, 128 degrees Fahrenheit. A world of extremes, and a lake quietly holding its shape at the base. Once researchers knew what to look for, the pattern multiplied. Over the next 2 decades, planes swept long lines across the continent, and satellites tracked how the ice surface rose and fell. A list of hidden lakes grew into the many hundreds. Some of them sit under the stable heart of the ice sheet. Others lie beneath fast-flowing ice streams that feed the coast. Observers notice something striking. Parts of the surface rose a few feet over months, then sank again. That rhythm meant lakes were filling and draining, as if a plumbing system was at work beneath the miles of ice. The continent's underside was not just a static freezer. It was a landscape of water moving slowly downhill, pooling, then releasing toward the sea. The idea of water under ice raises a natural question. What lives there? There is no sunlight under that much ice, no photosynthesis. The lakes are cut off from winds and dust that bring nutrients to surface snow. If anything survives, it must use chemical energy drawn from the rock and the water itself. That premise turned subglacial lakes from a mapping exercise into a biological mystery. You do not open a hidden lake casually. It has sat in darkness for a very long time. Everything about the approach must protect it from surface contamination. In the mid-1990s, scientists at a plateau station began deep drilling for climate records. The plan had been to stop well above any water. As the drill neared the bottom of the ice, the lowest layers in the core changed. Mixed within the clear ice were bands with unusual textures, not compressed snowfall, but ice that had formed from lake water, freezing onto the underside of the ice sheet. This so-called accretion ice, brought up in cylindrical cores, offered a preview of the sealed water below. Traces of organic material were reported in some bands. A few teams said they saw genetic material from microbes. Then others saw the telltale signatures of contaminants. The amounts were tiny. The debate turned on the limits of cleanliness in a drill camp, perched in the coldest place on Earth. A separate effort at a mountain-ringed lake farther west set out to open a hole directly into a small basin. Engineers prepared a hot water drill that would melt a narrow shaft down through more than 2 miles of ice, pipe water back to the surface, filter it, heat it, and send it down again, making a clean loop. Late in the year, they began. They had pumps, sensors, and a plan to keep the borehole balanced. Then pressure readings behaved strangely. Flow rates slipped out of expected ranges. Rather than risk a breach they could not control, the team stood down. It was a disappointment, but also a marker of a careful culture. Not all mysteries yield on the first try. The first clean window into a subglacial lake came closer to the coast, under the lower reaches of a fast ice stream. In early 2013, an American-led project used a hot water drill with multiple sterilization steps to open a borehole toward a shallow basin known from the surface rise and fall pattern. They collected water and muck from the bottom. In modest tents set against the wind, they ran tests. Under the microscope, cells were present, not in a lavish bloom, but consistently. There were tens of thousands of cells in a teaspoon of lake water. Further work suggested the microbes were alive. They seemed to be using iron, sulfur, and nitrogen compounds as energy sources, peeling electrons from minerals in the rock and cycling them through the water. They existed without sunlight and without plants, a kind of slow-motion chemical garden anchored in stone. Several years later, another team opened a path to a deeper basin farther inland, again with hot, filtered water and meticulous care. Water samples, slurries, and cores came up from the dark. Again, microbes. This time, mud from the bottom also held fragments that looked like the remains of small animals, bits of tiny crustaceans and other coastal organisms. It was unexpected in a lake so far under the ice. The leading explanation is prosaic and interesting at once. These pieces likely came from the margin where ice meets ocean, carried inland over time as the ice sheet flowed, then released from the ice near the bed. They were not living communities under the center of the continent, but reminders that the plumbing brings in more than water. Lake Vostok, the giant beneath the high plateau, keeps the most attention. Early in 2012, the deep borehole at the nearby station finally reached the lake. To prevent the drill from freezing, engineers had filled the upper shaft with a mixture of kerosene and antifreeze. When the bit touched the water, lake water surged up, met the colder fluid above, and froze into a plug. Samples carved from that plug later contained complex chemical mixes, and some teams reported genetic sequences they could not identify easily. Others ran the same tests and found traces consistent with contamination from drilling fluids and human presence. The balance of expert opinion leans toward caution. Until a clean, closed-loop system takes water directly, claims about unique inhabitants in that particular lake are premature. Theories about life under the ice cluster into a few families. One pictures isolation. Lakes cut off for hundreds of thousands of years, evolving quietly, building ecosystems almost entirely from chemical energy drawn from rock, water, and the slow grind beneath moving ice. In this view, the lakes are Earth's best training ground for understanding how a world like the icy moons of Jupiter and Saturn might support life without sunlight. The evidence for this model comes from the clean hot water projects. Those samples showed active microbes using minerals as fuel, slow but steady, a closed economy powered by the planet's interior heat and the chemistry of rock and water. Another model emphasizes connection. The lakes are part of networks. Water fills, migrates, and drains along shallow channels. An under-ice river system, as long as several hundred miles, likely links parts of the interior to the coast. The fill and drain cycles seen at the surface happen on time scales of months to years, not geologic ages. In this picture, nutrients, oxygen, and even fragments of marine life can be carried inland. Some lakes may be well oxygenated because freeze and melt cycles pump gases into the water over long spans. Others, farther from exchange, may be low in oxygen and more tightly constrained. The point is that sealed is not the right description for many basins. They are hidden, but not necessarily isolated. A third line of thought holds the door open for complexity. If a lake is oxygen-rich, supplied with a trickle of nutrients, and stable across long periods, could small animals persist there? Tiny worms, crustaceans, or something equally simple? No direct evidence supports a living community of larger organisms under the high interior ice. The fragments in the mud at one inland lake look like travelers, not residents. But the question remains a healthy one to keep on the table, to be answered by cleaner, better sampling. Skeptics focus on contamination and on statistics. Work in such cold, remote places presses equipment to its limits. Hot water drilling can be clean, but absolute sterility is a goal rather than a guarantee. Samples are few, and the biomass is low, which makes false positives from tiny bits of imported material worryingly easy. Early headlines about unknown microbes in deep lakes often faded under later scrutiny. The safest claim so far is also the most remarkable in its simplicity. There are living cells in water long cut off from the sun, and they are using the chemistry of rocks to make a living. If you lay the known facts out in sequence, a likely chain emerges. Pressure and geothermal warmth keep patches of water liquid beneath the ice. The bed is not a single smooth slab, but a gentle slope broken by basins and sills. Water pools in the basins, then spills to the next, and so on. Over months and years, some lakes fill and drain. Over longer stretches, under ice rivers trace paths toward the coast. Microbes inhabit the water, the sediments, and the wet film along the rock, eating minerals and breathing what the water offers. In a few places, oxygen slowly accumulates. In others, it is sparse. Shreds of coastal life get carried inland in the ice, then released as the ice melts at the base, becoming part of the sediment. Above, the ice's surface reflects the hidden motion, rising a little as water accumulates, sinking a little as it drains. The story holds wider implications. These lakes show that liquid water, sheltered from daylight and weather, can host life if there is a steady trickle of energy and a place to stand. That is a quiet lesson with reach beyond this planet. At the same time, the lakes caution us about easy answers. Hidden does not mean untouched. Sealed does not always mean isolated. A chain of lakes and channels beneath a continent is a complicated environment, and most of it remains unvisited. There is more work planned. Engineers have refined clean drilling methods that recirculate, filter, and heat the water without adding chemicals. The plan is simple in outline and hard in practice. Open, sample, close. Bring up vials of water and short cores of sediment, then retreat and let the whole freeze again. Future studies will measure the energy sources in detail, not just iron and sulfur, but the full menu of compounds in the water and the rate at which microbes use them. They will watch the lakes breathe, filling and draining, using satellites that track the smallest changes in height. They may one day return to the giant under the plateau with a cleaner approach. So the samples are a true measure of a place that has sat in darkness for so long. For now, imagine a black lake under 2 miles of ice. The water is near the freezing point, dense and still. A cell divides once every few weeks in a tiny pocket of sediment. A small air bubble rises and disappears into the underside of the ice, adding a breath to whatever lies below. Above it all, the plateau stays firm and white. The surface air rolling from minus 40 degrees Celsius to minus 70 and back, from minus 40 degrees Fahrenheit to about minus 94. Nothing loud happens here. And yet, quietly, a hidden ecosystem turns over its small ledger, sustained by rock, by pressure, by time. The sky should have been blank, The water flat, the sea floor as nondescript as a chalkboard wiped clean. Instead, a circle appeared where no circle should be, and a long mark trailed behind it as if something had skidded and come to rest. The screen glowed on a small ship between Sweden and Finland in the summer of 2011. And with that, the story called the Baltic Sea Anomaly Revisited began. The place was the northern Baltic, far from shipping lanes that fishermen favor and tourists cross. A Swedish salvage crew was sweeping long lines back and forth, sending sound pulses down to map the bottom while they searched for old wrecks and forgotten cargo. The water there is not deep by ocean standards, but deep enough to keep secrets. The bottom lies around 90 meters down, nearly 300 feet, where the temperature hovers near 4 degrees Celsius or 39 degrees Fahrenheit year-round. They had crossed an empty patch dozens of times already when the return suddenly sharpened and thickened. An almost circular feature came up on their display, about 60 meters across. The surface looked rough, with repeated lines like steps. Behind it, along the direction of the boat's path, a darker line extended several hundred meters, like a wake frozen into the mud. The crew saved the pass, turned back, and ran the same line again. The circle reappeared. The long line showed up too. They made more passes from different angles, speeds, and heights above the bottom. The shape held. In a field where old bottles and driftwood often look like coins and ropes, it is uncommon to see a clean circle hold its place across repeated views. News moved fast. An unnamed formation in the northern Baltic is not usually news, but a circular object with a trailing mark is hard to ignore. The images went wider than the crew expected. The early picture, grainy, high contrast, with a surprisingly sharp edge between object and seabed, tilted toward drama. In the months that followed, commentary bloomed. The salvage team kept the exact location close and planned a dive. They returned a year later with a small, remotely operated submersible and divers. The dive reports were matter-of-fact. Visibility was poor, a meter or two. The water was pitch dark, cold, and quiet. The divers descended along a line and felt the bottom before they saw it. Their lights picked out a dome-like rise that stood a few meters above the surrounding seafloor. The surface of the rise looked hard, not muddy. Parts of it had a layered look, like broad steps, but irregular and worn. The top of the dome was not perfectly flat. It had shallow undulations and fractures. At one spot, stones the size of fists sat in a rough ring, darkened as though burned. The divers examined them gently. They were cold to the touch, of course, and crumbled at the edges like old rock. The ring, if it was a ring at all, was easily explained by gravity on a slope. There were small frustrations. Cameras blinked out, then returned. A satellite phone glitched on deck. Those hiccups grew larger in later retellings. Electrical issues on a small boat in brackish spray, in the cold, are not rare. Battery performance drops quickly at 4 degrees Celsius, 39 degrees Fahrenheit. Connectors corrode. Salt air creeps where it can. But on a story like this, even a normal malfunction feels like part of the script. Samples were taken. Fragments of the darker stones and chips from the hard surface of the rise itself went to a laboratory in Stockholm. The first look under a microscope, and with simple chemical tests, suggested volcanic rock, likely basalt or something similar. In that region, the bedrock is ancient and varied. Ice sheets have scraped across it many times, grinding, carrying, and dropping stones from far away. A dark coating on the sample matched iron and manganese oxides that commonly stain boulders sitting at the bottom for long periods. In plain language, old rock, probably moved by ice, with a long soak in cold water that leaves a black skin on it. Useful, but not spectacular. The crew ran more sound sweeps. Each pass drew the shape a little differently. Edge sharpness changed with angle. Shadows lengthened or shrank depending on the distance from the bottom and the speed of the sweep. The rough stare effect was far less dramatic when seen up close compared to the early images. The long trailing line behind the object was not a single groove. It seemed to be a depression with scattered stones and lighter sediments arranged in streaks, as if currents or past movement had sorted grains and pebbles along one direction. If you put the facts on a timeline, a clearer picture emerges. Summer 2011. A circular hard rise, roughly 60 meters across, at about 90 meters depth, with an elongate low behind it. Early 2012. Divers observe a dome with uneven ledges, no metal debris, and no obvious sign of machinery or construction. Samples indicate volcanic rock and common seabed coatings. Later sweeps show the same shape, but without the crisp geometric look of the first image. What could it be? The common explanations come first. The Baltic floor bears the handwriting of ice. During the last glacial maximum, a sheet a mile thick moved across these latitudes. It pressed and plucked, smoothed and fractured bedrock below. As it melted, it littered the area with erratics, boulders from distant quarries, and started the long present-day rebound of the land. In such a landscape, round bedrock knobs are ordinary. They can look like low domes, their upstream faces worn smooth by ice, and their downstream sides broken into steps where the ice pulled blocks away, following natural cracks in the rock. Seen from above, with a sound-based image, the combination, dome plus blocky steps, can read as a circle with repeated lines across it. Hard rock has a stronger echo than soft mud. The border between the two can look like a clean edge, even when it is a slope. And the long, dark trail might be a swale, a trough where finer sediments settle, aligned with the direction of the latest prevailing currents, or an ancient channel carved under ice. It could also be the remnant of a trawl pass from commercial fishing years ago, now softened by time. Another practical model places the anomaly within a field of glacial stones cemented together by minerals. Cold, low-oxygen water promotes the slow growth of iron and manganese coatings on rock. Over centuries, neighboring stones can appear fused by thin layers of dark crust. Divers in the region have reported many boulders covered with a black film, like soot on a fireplace. The burnt appearance of the small stones on top of the rise is consistent with this. No heat is required, just chemistry and time. The more human theories always arrive. A turret base from a lost warship, a concrete foundation for a vanished lighthouse, a ceremonial circle from a period when the sea was lower and the place was dry land. Even for those who look far afield, a craft from somewhere else. Each offers a reason to find order, right angles, clean lines, intent in a rough landscape. The counterpoints here are steady. The dives did not show any metal plates, bolts, or reinforcing bars. No cables, no planks, no fasteners, no signs of deliberate shaping. Magnetic readings were not presented as significant by the team, and if a large metal structure lay there, they are unlikely to have missed the chance to say so clearly. Lists of known wrecks do not place a large circular object at that spot. And if a ring of stones is seen on a slope of broken rock, the simplest reading is that falling pieces found a small shelf and stopped. There is also a family of explanations that invokes gas. In several seas, methane bubbling up through sediments makes pockmarks, and sometimes mineral deposits harden around vents. Could the dome be a cap formed by mineral-laden water? The samples argued against that. The recovered chips were hard, volcanic rock, not a soft crust precipitated from gas-rich fluids. And the site did not show a field of pits and mounds the way active gas areas usually do. One detail worth keeping is the way imaging can mislead. When a ship tows a sound source, the distance to the bottom, the speed over ground, and the angle of the beam all matter. A small change in any of those exaggerates edges, stretches shadows, or rounds corners. The first picture that made headlines, the one that seemed to show a near-perfect disk, was a single pass at a particular angle and distance. Later passes from other angles made the edges less clean and the lines less straight. That is not deception. It is a known property of the tool. It is also, in a sense, why the image worked on the public imagination. One view made the ordinary look precise. As for newer developments, the years since the first dives have been quiet. No high-resolution maps from independent parties have landed in public archives. No agency has published a recovery plan or filed a claim. The crew who found it have spoken of returning with better gear and funding. Their updates were sporadic. Researchers who examined the few samples available stood by their initial impressions. Old volcanic rock, likely moved by glacial action, sitting in a sediment field that tells a slow, cold story. None of this forbids surprise. The Baltic still hides wrecks under sandbars and stones under silt. But when you lay out the puzzle pieces we have, the size, the depth, the dive reports, the composition of the samples, the behavior of the imaging, the most probable chain runs like this. A bedrock dome, or a pile of glacial stones, rises a few meters above a soft bottom. The dome is fractured into broad steps along natural cracks. Over time, iron and manganese coat exposed surfaces, turning them dark. Fine sediment drapes and settles in a long swale behind the dome. A salvage crew, moving at just the right speed and angle, captures a dramatic view that looks nearly geometric. Up close, the geometry softens back into geology. There is one last point to touch gently. Stories have a way of outgrowing their facts, especially when early pictures take on a life of their own. Some retellings leaned into the extraordinary and left the ordinary behind. If there is uncertainty here, it is the daily kind that comes with imperfect data, not a secret being guarded by force. Without a complete, peer-reviewed map and a suite of clean samples, mystery has room to breathe. But mystery also yields a little when you hold it up to the ground truth of rock and ice. So picture the place now. Cold, brackish water at 4 degrees Celsius, 39 degrees Fahrenheit, sweeping a low hill in the dark. A brittle coating on stone glints under a diver's lamp. Silt lifts, settles, and smooths sharper edges. Above, a small boat idles as the crew watches a screen, the return moving from left to right like a slow heartbeat. On the bottom, the circle waits, not a perfect disk, not a machine, but a stubborn shape left by time, ice, and minerals, carrying just enough symmetry to catch the eye. And for now, that is enough. Most encounters fade as quickly as they arrive. A sound across a field, a light that doesn't belong to any star, and then a return to ordinary life. But sometimes events gather quietly from house to house until an entire region is looking up. This is that kind of story. The impossible drones of 2019, the Colorado-Nebraska incident. It began in the short days before the new year, when the nights came early and stayed late. Out on section roads that divide the plains into neat squares, people in northeastern Colorado started noticing bright points moving with purpose. The air was cold enough to sting, often below -5 degrees Celsius, around 20 degrees Fahrenheit. And the sky was clean, a kind of winter clarity you get on the high plains. One light became several. By the end of the week, farmers, teachers, truck drivers, and sheriff's deputies in neighboring counties were all seeing the same thing. Groups of lights moving in straight lines and slow turns, holding their height as if following invisible lanes. The first calls clustered in Phillips and Yuma counties. Then reports spread across Washington, Sedgwick, Morgan, and Lincoln. Within days, the pattern reached over the state line into the western counties of Nebraska, Dewell, Perkins, Chase. The time window repeated itself night after night, early evening to close to midnight, sometimes later. Witnesses described 6 to 10 objects at once, sometimes more, moving at a steady walking pace across the sky. Some believed they could hear a low electric buzz. Others swore the lights were silent. A few said one seemed larger than the rest, as if a lead craft were guiding smaller ones. What made these sightings hard to ignore was the way people described the behavior. The lights didn't wander. They ran lines mile after mile, then turned, ran another line, and turned again. A grid. At times, the objects seemed evenly spaced across the sky, like the marks on a ruler. Many had a bright white strobe and a steady red or amber glow. Several witnesses thought they could make out the shape against the night. Not a little hobby quadcopter, but something with a span about the size of a tall person, wings stiff and straight, circling without a wobble. Sheriff's offices tried to keep the temperature down. They posted simple notices. "We know you're seeing these. Please don't shoot at them. Don't chase them across frozen fields. Call if you can get a clear photograph or a license plate near a suspected launch site." Deputies drove gravel roads, headlights sweeping ditch lines and pasture gates, looking for a van, a trailer, any sign of an operator. Many nights, they saw the lights themselves, hanging above the flats and then sliding north or east in that same unhurried way. No debris on the ground, no obvious takeoff points, just lights holding a few 100 feet of height over winter stubble and center pivots standing still. After the new year, with the story running in national outlets and social media amplifying it further, county leaders met in a drafty hall at the edge of a 2-lane town. More than 50 officials gathered: sheriffs, emergency managers, state public safety staff, and a few federal liaisons who had made the drive out. They traded times, maps, and photographs that mostly showed darkness and dots. They agreed on a practical list: collect exact locations, note direction of travel, compare against known air traffic, ask nearby bases, power companies, and pipeline operators if they had ongoing flights. A small joint group formed to centralize reports. Aircraft went up. The state's own surveillance plane, usually tasked with fire spotting and search and rescue, flew a late-night pattern. A federal enforcement aircraft with a full suite of sensors made a pass as well. Deputies parked under the paths and called bearings by radio as the lights crossed above. But when the data came back, it was thin. The state plane did not capture drones on its cameras. The federal plane recorded heat from farmhouses and trucks on county roads, but did not lock on to a swarm of small craft. Ground teams following individual lights lost them along the horizon, where red beacons on distant towers blended with stars and aircraft. Theories spread as quickly as the sightings. Some seemed to fit the observed behavior. Mapping contractors sometimes fly long-endurance fixed-wing drones in precise grids to survey farmland or assess storm damage. Pipeline companies hire pilots to inspect rights-of-way. Railroads do the same for track. The lights and steady lines echoed those jobs. The counterpoint was scale. Flying a handful of large, night-capable drones across multiple counties night after night would take permits, insurance, and staffing, or a remarkable disregard for both. When asked directly, the major companies working in the region said they were not involved. The military explanation arrived next. The plains here are edged by missile fields, managed from just over the state line to the northwest. There are also training areas, radar stations, and long, flat corridors that run right up to the foothills. Could this be an exercise? A test of counter-drone systems or swarming tactics? The officials in uniform who attended the county gathering said no. No scheduled operations. No tests announced or hinted. And if an exercise had been running, someone would have needed to deconflict airspace and coordinate with the federal aviation regulator. There were no such notices for the area on those nights. Many reports were more ordinary once you looked closely. Winter skies can trick the eye. A bright planet low in the west can appear to follow you down a road. A light on a tall communications tower, seen from a new angle, can look like it is moving until you triangulate it with a fence post. Several times, deputies chasing a red and white blink across the horizon ended up under a small, single-engine airplane, cruising its own grid at a couple of thousand feet. Flight records checked later matched those tracks. One widely circulated account of a mothership leading a formation faded under scrutiny. There was no independent confirmation and no aircraft caught on camera that matched the description. A state public safety summary, released months later, when the fields had turned green and the story had cooled, tried to pin the puzzle down. Investigators collected nearly 200 reports and sorted them by quality and detail. The findings were plain. Some witnesses likely saw planets and stars. Some saw manned aircraft flying regular patterns. A few saw hobby drones, the kind bought as holiday gifts, that happened to be in the air on the same nights and added to the impression of a larger operation. And yet, not every report fit cleanly in those bins. There were still clusters where multiple trained observers described the same group behaviors at the same time. There were nights when people spread across two counties called in near identical grids that seemed to advance over the prairie like a slow-moving checkerboard. Photographs and video were surprisingly scarce and unclear. A statement, perhaps, about how hard it is to capture small moving lights at night, even in an age of good cameras. One detail that confused and then clarified things involved scale. From the ground, a fixed-wing drone flying a few hundred feet up, with a wingspan near 2 meters, can present as much larger than it is, particularly if you only see its lights. A manned aircraft at several thousand feet can look smaller than you expect. Misjudging height by night triggers misjudgments of speed and size. Someone seeing a neat trio drifting 10 miles away might imagine a dozen roaring overhead. When neighbors share those impressions in real time, the mind starts to complete the picture. If you lay the story out as a timeline, it acquires a steady rhythm. Mid-December, first clustered reports in northeastern Colorado. Late December, multiple counties seeing groups of lights, usually between early evening and midnight. Grids described, sizes estimated at the span of a tall person or a larger. Early January, a surge of calls, regional coordination, aircraft launches, and public meetings. Mid-January, activity tails off. In some places it stops entirely. Spring, a sober, inconclusive state summary that names many ordinary causes and leaves a small remainder in the unknown column. So what is most likely? The practical chain goes like this. One or more operators, perhaps surveying fields or critical infrastructure, flew long-endurance fixed-wing drones at night, running precise patterns that hugged county roads and property lines. A few nights of that, witnessed by people unused to seeing large drones after dark, generated talk. Meanwhile, small airplanes flew their own routes, pipeline patrols, training runs, and appeared to join the pattern. Bright winter planets sat low in the sky at just the wrong angle. Hobby drones, newly unwrapped for the holidays, added another layer. The story grew in the telling, as stories do, especially across flat land where neighbors are miles apart but share the same sky. When attention spiked, the true operator, if there was one, likely paused. The remainder is a mixture of memory, incomplete video, and images that prove how deceptive night can be. There are other more exotic ideas, a deliberate test of how communities respond to unknown craft. A private technology demonstration away from major air corridors. A foreign entity probing fields and silos along the high plains. Each carries a certain charge. Each runs into the same wall. No firm evidence surfaced. No recovered hardware. No responsible party, public or private, stepped forward when asked. The Air Defense Command in the mountains to the south said it was not tracking unknown swarms over the plains on those nights. And the federal regulator did not produce waivers or filings that pointed to a sanctioned program. It is worth noting one last thing, and it sits near the edge of this kind of tale. In the months after, some of the most dramatic accounts evaporated under a closer look. A few were hearsay. A few were second-hand summaries of social media posts already misreading what earlier witnesses had said. This does not mean nothing flew. It means the simplest chain carries the most weight when the lights go out and we are left with fragments. By the next winter, if you drove those same roads after supper and cut the engine to listen, you would hear what you always hear there. A far highway, a grain elevator cycle, a dog 3 farms away. The sky would be clear and cold, minus 10 degrees Celsius, or 14 degrees Fahrenheit on a tough night, with a planet pinned over the horizon and a passenger jet sliding high, its lights flicking at a measured rate. Somewhere, a tower would blink red over a dark field. That's the last image this story leaves you with. A plain sky, a few moving lights, and a memory of a grid that may have been part machine, part expectation, and part the old habit of people to look up together and try to make sense of what they see. To the few who watched from the road, it felt sudden. A lantern swinging in the dark, a wooden tripod against the stars, and blocks that should not have moved answering to a single man's hands. The place he was building would come to be called the Coral Castle. South of Miami, a little inland from the coast, there is an enclosure of pale stone that looks both stubborn and precise. It grew over decades, piece by piece, under the care of a slim man from the Baltic countryside named Edward Leedskalnin. He was not tall. His clothes hung loose. He kept to himself. But around him, stone rose in clean lines and clean circles, as if the ground itself had agreed to cooperate. The story begins in the early 1920s, in a scrubby patch near Florida City. Edward set up a shack and began cutting blocks from the local bedrock, which is a porous limestone formed from ancient coral. It is lighter than granite, but not by much, and it writes a hard sentence when you try to lift it. He called his place Rockgate Park. He worked mostly at night by lantern. During the day, he gave small tours and charged a coin for entry. On his best afternoons, he acted as a guide, with the soft energy of someone who has already done his best, talking to the stone itself. Visitors saw walls 8 feet high, made of blocks fitted without mortar. They saw a crescent moon carved from Megal slabs, a heart-shaped table, rocking chairs for two, and a throne room set out with a tall seat for a king, a shorter one for a queen, and a narrow chair for a child. A sundial ticked the hours with surprising accuracy. A telescope stone aimed at the North Star. With each new season, more pieces appeared. A fountain shaped like Saturn, a bathtub carved straight from bedrock, a stair that moved none of its weight into vanity. The material for all of it came from the ground a step away. Edward quarried the bedrock and freed blocks sometimes taller than a person and many times heavier. He eased them onto rollers and moved them through narrow paths. No one saw a big crew. People said they only ever saw him. He wore a hat. He had a quiet wave for those who stopped by. When anyone asked how he did it, he said he had found the secret of the old builders. And he left it at that. By the mid-1930s, he made a decision. A new highway and new homes were pressing toward his fence. He chose to move. He bought a small tract of land, roughly 10 miles away, near Homestead, and began to ship the castle, piece by piece, to the new site. He hired a truck. The driver would arrive at the gate. Edward would ask him to step aside for a while, and when the driver returned, the bed of the truck would be loaded with stones that no one had watched go up the ramp. This happened more than once. After each journey, Edward worked nights to raise the walls again, reseat the tables, lift the crescent, and hang it so that even a breeze could play in its curve. The newer site is the one people visit today. Altogether, the mass of the place is measured in the low thousands of tons. Some individual stones weigh near 30 tons. The walls are thick and steady, their edges dressed by hand. The best-known piece is a gate, a single slab nearly 10 feet tall and weighing about 9 tons, hung so precisely on a hidden bearing that a child could push it open with a fingertip. For decades, it swung in a perfect arc. When it wore down and stopped turning, repair crews cut it open and found a metal shaft and bearing set with a care that hinted at machine shop skill. They replaced the parts and the gate turned again, though never with quite the same ease. The magic, if there was any, seemed to have been the exact balance more than the parts themselves. There is a personal line under the stones. Years before he moved to Florida, Edward had been engaged to a woman he called Sweet 16. The wedding never came. He left his old life and crossed the ocean. In Florida, he built alone. He marked some stones with her title. He guided visitors to a heart table and a pair of chairs and told them simply that he had made the place for her. He did not say her name, and there is no record that she saw it. What remains is that he never married, and each part of the site seems arranged with a private logic, as if he were hosting a guest who might arrive tomorrow. The core mystery is practical. How did he move and lift the stones? The answers, depending on whom you ask, either sit in plain sight or remain locked away in his notebooks. On the ground after his death, people found chains, a set of sturdy pulleys, jacks, and a flywheel device in his workshed made from a salvaged gear wrapped with wire and horseshoe magnets. Several photographs from his lifetime show tall tripods built from telephone poles, with block and tackle rigs slung from the apex. The bearing inside the famous gate was a truck axle and a top bearing set into the overhead lintel. In one stone, you can see a neat hole bored right through the center, the kind of hole you would need if you wanted to seat a shaft perfectly in line with the stone's balance point. Engineers who have studied the site point to the basics of leverage and time. A tripod and pulley arrangement can multiply a person's effort many times over. A block supported in a cradle is easier to inch forward than a raw mass on dirt. If you are patient, if you move 1 inch at a time, if you know where a stone's center of gravity lies, you can do things that surprise people who expect speed instead of persistence. In demonstrations elsewhere, artisans have shown how to stand monoliths using logs, counterweights, and even small seesaws built under the rock itself. A single person directing a few simple machines can achieve a great deal. And Edward, as far as anyone can tell, had years, not minutes. Against that are the stories that keep the coral castle in the category of something more. Neighbors said he worked in the dark so no one could copy him. Children claimed, years after the fact, that they saw stones that looked like they floated for a moment before they settled. Visitors listened while he explained his view of magnetism. He sold small pamphlets on magnetic current and came away believing he had found a way to cancel weight. He himself liked the idea that there was a secret. He would walk tour groups to a spot under the telescope stone and say something gentle about how everything has two sides, how invisible forces can push and pull, and how the builders who came before us knew more than we give them credit for. The most cited explanations sort themselves into a few groups. The first is the straightforward one: careful engineering and relentless labor. Supporters of this view point to the photographs of tripods, the pulleys, the metal shaft found in the gate, and the cut marks on the stones that look exactly like what you get when you run abrasive across limestone with a simple hand drill. They note that Miami's oolitic limestone, while heavy, is just workable enough for a patient person with iron tools. They remind us that the 9-ton gate was not weightless. It was balanced on a well-placed axle. The second theory suggests he had help, and chose not to mention it. This argument proposes that a few late-night laborers, paid in cash, could have shifted the blocks under his direction. The obstacle here is the number of people who came and went over the years without offering a firm account and Edward's own personality. He liked control, and he seemed to prefer doing things alone. The truck driver who carried the stones during the move never named a secret crew. He only said that each time he came back from running an errand, the cargo had somehow loaded itself. The third theory leans toward the exotic, that he found a way to use magnetism or some unknown principle to lessen weight. This line of thought loops back to the magnets in his workshop, the flywheel in the shed, and his confident claim that he had learned how the old builders did their work. The counterpoints are practical. No measurement on the site shows anything that behaves outside the rules. The flywheel is consistent with a hand-cranked generator. The magnets are of the type common in the early 20th century for demonstrations and small experiments. And when one of his signature pieces, the Great Gate, finally gave up and had to be taken apart, it revealed a very human solution: an axle, a bearing, a drilled hole where balance beats spectacle. There are a few lesser ideas, including hidden cranes and underground rails. The ground today does not show a buried track, and if a large powered crane had stood there regularly, more people would have seen it. What they saw, overwhelmingly, was a man working under lantern light, a few tall tripods, and a pile of hand tools. If he buried anything, it was his methods behind a habit of not explaining them. One detail worth weighing against the myths is how well the coral castle has held up against weather. When a severe hurricane came through in the early 1990s, tearing roofs off houses and pushing cars into fences, the coral castle survived with only minor damage. Walls held in place. Sculptures stayed where he had set them. That is less an argument for the supernatural and more a statement about the site's balance and the way weight can become an ally once it is where you want it. So which chain of events seems most likely when you lay out the facts in order? A man with time and a fixed idea arrives in South Florida and finds a material he can shape. He teaches himself where to cut and how to lever. He builds tripods from straight poles and hangs block and tackle rigs that multiply his strength. He studies balance until a 9-ton slab behaves as if it weighs a few pounds when pushed at just the right point on just the right bearing. He works at night to stay cool and to keep his methods to himself. He moves his work a few miles when the neighborhood crowds in. He opens the gate for visitors in the afternoon and tells them with a small smile that he knows a secret. He writes a slim booklet about forces and keeps the practical tricks in his pocket. There is a softer truth beside the mechanics. People needed the idea that one person could make something so large with only determination and a set of honest tools. Edward never contradicted them. He let the place stand as both evidence and invitation. If you understood the sky well enough to carve a telescope hole toward the North Star, if you could count the sun's arc well enough to cut a working sundial, perhaps you could also work out how to slide a 30-ton block through a narrow gate. And if you could not, he was happy to sell you a ticket and a story. He died in the early 1950s after taking a bus to a hospital and leaving a note at his gate asking visitors not to come in while he was away. He was buried nearby. The site passed to family and then to new owners, and today it is a museum. Guides still point to the 9-ton gate, to the heart table, to the telescope stone, to the chairs for a queen and child. They tell you about Suite 16, and they tell you about the night work, and then they stand back and let you decide. At dusk, when the tours thin out and the air cools, the walls keep their own kind of quiet. The stones hold their line. The sundial throws a clean shadow. The gate, whether it swings that day or not, looks ready to. If you stand by the fence and wait, you can almost see the lantern moving again, circling a tripod, pausing at a pulley, while a person you can barely make out sets his hands on a block and makes another inch of progress. A hardpan basin, a ridge of pale limestone, and a narrow door set deep into the rock. No sign, no crowd, just the thin cry of a desert bird and a lock that yields to a key very few people hold. Inside, a staircase corkscrews down and a machine waits for noon. This is the 3,600-year clock in the desert. On the maps, the site sits in the high desert of far west Texas, a dry region of yucca, ocotillo, and long views. Summers push toward 40 degrees Celsius or 104 degrees Fahrenheit by afternoon, then give back a clean chill at night. The mountain is private land, and the entrance is cut straight into it. The builders began speaking in public about the idea in the early 1990s. A computer designer named Danny Hillis said he wanted a clock that could keep time for 10,000 years, and a writer named Stuart Brand echoed the point. Get people to think in longer spans than an election cycle or a quarterly report. Over the next 2 decades, they built prototypes to explore the basics. One reached the Science Museum in London, ticking with a simple, slow grace. Another test site sat in the Nevada desert. Then, deep excavation began in Texas. The land belonged to Jeff Bezos, who backed the project and let the mountain be hollowed and shaped. In early footage released years later, you can see the precision. A shaft hundreds of feet deep, a helical staircase carved into the stone, enormous gears lowered in pieces and pinned together underground. Then the door closed again, and public information thinned to a handful of press notes, scattered interviews, and a few still photographs of machined metal in a chamber lit by work lamps. The core claim is plain. This clock is purely mechanical. No batteries, no software, no touchscreen panel waiting for a reboot. It uses materials that shrug off corrosion. It prefers simple motions, pushes and pulls that do not rely on oil films that could dry out, or seals that could crack in a decade. At solar noon, a narrow shaft of sunlight sneaks into the mountain and hits the heart of the mechanism. That daily bright line sets the machine back to truth, correcting any slow drift the way a sailor once set a timepiece by the sun. There are other practical details, some confirmed, some inferred from prototypes. Weight provides energy. Visitors, if someday visitors are allowed, would wind the clock by walking and turning handles, storing potential in hanging stones. The desert heat itself helps. The day-night swing, often more than 20 degrees Celsius or 36 degrees Fahrenheit between afternoon and dawn, flexes metal and can be harnessed to lift a small weight a few inches at a time. This slow harvest keeps springs under tension and lets the machine tick forward one day with each sun and star. Inside, dials do not count minutes. They count bigger things. One face marks the year. Another leans on older rhythms. The drift of solar noon through the seasons, the long dance of the planets across the ecliptic. A chime machine rings a short melody at each noon, and no melody should repeat within any human lifetime. The mathematics behind that, millions of combinations, was worked out over long nights at a workbench, then tested on brass models that you can find in older talks if you look long enough. The sound is not for timekeeping. It is for arrival. Imagine stepping into the mountain and hearing a tune that no one has heard before. So why call it the 3,600-year clock when the designers often say 10,000? The nickname comes from the number that sits at the base of how we tell time. 60 seconds to a minute, 60 minutes to an hour. 60 by 60 is 3,600. Long before wristwatches, the builders of the first city clocks counted by 60s. In older clay texts from the river plains farther east, a unit called a sar meant that same 60 times 60. The team behind the desert clock nodded to that inheritance in ratios and gear counts, and among the small circle of people who followed the project closely, the nickname stuck. 36 centuries is not the machine's full ambition. It is the size of a unit you can feel, longer than empires, shorter than the ice. Whatever you call it, the practical mystery is bigger than a name. Can a device survive that long? Dust creeps into everything. People chip what they touch. A goat can do more damage than a careful saboteur. To answer that, the builder set strict rules. Keep the working simple. Use stone, steel, and ceramic. Avoid grease. Allow for slack that temperature can forgive. And most of all, design a reset. The sun at noon is a standard no calendar can argue with. If a war or a quiet century passes and the clock stops, the next human who winds it should not need a manual. They should walk, watch, and listen until the mechanism aligns itself to the sky again. We can place some exact moments in the timeline. In the late 1990s, a guest at a talk in San Francisco heard the first public declarations, a clock for deep time. In the early 2000s, a prototype in London began ticking, with visitors working the winding wheel into habit. In the early 2010s, reports put crews on the Texas mountain, opening a vertical shaft and cutting the internal stair. The first large gear assemblies arrived shortly after, hauled up switchbacks, and lowered into the void. In a short video released a few years later, you can pick out the gleam of a tall escapement in a stone-walled chamber. After that, silence. No open hours, no ribbon. For a modern project backed by a famous name, the quiet landed and stayed. From that quiet grew the second mystery. What else is inside? Your first group says there is nothing secret to guess at. They call it exactly what it appears to be, a timekeeping experiment designed to change how people think. The evidence is straightforward. The foundation behind the project has published essays about slow work and long-term stewardship for more than 25 years. They run a library, support a language archive engraved on microsurfaces, and keep a public lecture series going on topics that stretch beyond a human life. An unhurried clock fits those habits. A different group treats the clock as sculpture with gears. They admire the engineering, but see the mountain as a monument first, a statement meant to be looked at rather than used. Behind this is the obvious fact that few will ever visit. The approach is remote. The door is not open. If the real goal were to calibrate a community to longer spans, why not place the machine in a public hall or on a city hill where school groups could wind it on weekends? A third line of thought edges toward storage and safekeeping. People note the thick stone shelter, the stable temperature inside the mountain, and the builder's interest in knowledge that can outlast devices. They wonder if the clock shares space with sealed canisters, seeds, texts, code carved not into silicon, but into substances that resist heat and time. There are precedents elsewhere: seed banks under Arctic ground, archives of languages etched into disks. But there is no public record of such a vault in this mountain. The counterpoint is simple. When the same group built their language disks, they wrote broadly about it. No similar admission exists here. There is also the noise you get around any closed door on private land in a remote place. The mountain sits in a region where rocketry firms test engines in the distance. Some online maps draw lines between the clock, launch pads, and other projects that share a benefactor. The clock becomes a totem in those telling, part of a pattern, a code laid into the landscape. Back on solid ground, nothing connects it to flight besides the name on neighboring deeds. The technical skepticism is more interesting. Makers and watch restorers will tell you that every mechanical thing needs attention. Springs fatigue, bearings wear. Even a dry, lubricated pivot will polish a soft spot over thousands of cycles. The people behind the clock acknowledged this in their earliest notes. They do not promise magic. They design for maintenance in long intervals. A century hand that moves once in 100 years does not grind with the same urgency as a second hand. If a visitor every few decades can replace one part or clear out dust, that is enough. What defeats many machines is not time itself, but a cascade of small faults that gather when care stops entirely. One rare detail, easy to miss, lives in the choice of pace. The clock does not try to mark every moment. It waits for noon. At that instant, a beam of sunlight, thin, sharp, and always honest, enters a chamber and lands on a sensor that is not electric. That cue moves a cam, and the clock steps. In overcast weather, the machine idles without harm. The next clear day corrects the drift. The result is a device that needs the sky more than its visitors. It is less a master than a polite student of the sun. Is it finished? It depends on what you mean by finished. Parts are installed, the shaft is lined, the stairs are carved and safe. A video showed a giant wheel turning and a long rod lifting a weight in a smooth, patient stroke. But a full opening, a busy schedule, a ticket you can buy, that remains out of reach. Perhaps that is deliberate. The concept never promised a spectacle, it promised a standard. The clock's best work might be done in people who never see it, who hear that something under a desert mountain is built for someone centuries from now, and decide to plant a different kind of tree, start a different kind of project, keep a promise that would be easy to break. As for the number in the title, a span of 3,600 years, take it as a human handle on a larger idea. In many old counting systems, that is a complete square of time, 60 by 60. It is a unit not often used in daily life, but it is a clear shape you can hold in your head, a long breath between the present and descendants who might know your name only from a list. In that distance, a clock that waits for noon and moves once per day makes sense. Picture the chamber as the desert heat lets go after sunset. The air cools by 10 or 15 degrees Celsius, or 18 to 27 degrees Fahrenheit. Metal pulls in, stone keeps its calm, and a small weight rises a fraction of an inch on a winding drum. Outside, wind brushes creosote. Inside, there is no rush. Tomorrow at noon, a thin rod of light will find its mark, and the machine will accept the correction without argument. The melody will be one nobody has heard. The stairs will still be there. The door will hold. And somewhere, far from the mountain, someone will remember that a clock is waiting and that not every day has to be measured in seconds to matter. And so, we've listened to the ocean's deepest pulse, followed 2 lost spacecraft beyond the sun, and traced a cold scar across the map of the universe. We've looked under ice, across seas, and into skies where light moves in ways no flight plan explains. Each of these mysteries leaves a quiet echo, not of fear, but of perspective. A reminder of how much still waits in the spaces between what we know. As you settle deeper into rest, let the questions drift too, not for solving, but for holding softly, like stones at the bottom of a river. Tomorrow they will still be there, waiting. But for now, the mysteries can keep watch, and you can let go. Good night, and thanks for letting me keep you company.